Hello, and thank you for attending my presentation. My name is Griffin Cherrill, and this paper was written by myself and Michael Don of Victoria University of Wellington. A thermal bridge can be identified as a change in the thermal resistance of the building fabric where it would otherwise be uniform. For example, a timber stud that sits within the insulation layer. To avoid internal moisture, the minimum R value of a timber-framed wall is R1.5 as prescribed by Clause E3 of the New Zealand Building Code. This R value is calculated by area weighting the thermal resistance of each material using the equivalent U value method. This method does not allow for surface temperatures surrounding larger thermal bridges such as 270 millimeters timber allowed by New Zealand Standard 3604 to be assessed. Instead, it encourages the problem of excess timber to be solved by increasing the thermal resistance of insulation. A systematic literature review was conducted to obtain relevant literature relating to the assessment of thermal bridges and the risk of condensation. The process for the review was taken from Boland et al. 2014. When compared to a narrative review, the systematic process follows an explicit and rigorous methodology that allows a third party to carry out the same process and obtain the same papers. It reduces the risk of bias from the author, which could influence the papers that are collected, and increases the chance of collecting all relevant literature. The replicable methodology also means there is justification into why some papers were not collected or identified. The systematic process starts by making a PICO table to establish the aim of the literature review and the keywords that would be used to search the databases. The review is aimed at single-family timber frame houses that comply with Clause E3, but are also expected to be at risk of condensation due to built-up timber. The intervention of the baseline approach from Clause E3 is the use of a more comprehensive calculation tool, and the comparison is between the factors that increase the complexity of a tool and the results produced. The outcome of the review is to identify whether the method from Clause E3 is sufficient, and if not, what does a tool need to do to reliably assess the risk? The keywords at the top of the table were put through a number of databases with the results shown in the table. The relevant literature from each database was collected, shown in brackets. After, the screening process removed the number of relevant references from 136 to 32. This process included removing duplicates, obtaining full-text papers, and applying an exclusion criteria. The findings from the literature review confirmed the initial suspicion about the method used in Clause E3. Mao and Johannesson identify how the thermal bridges changed local surface temperatures and increased the risk of condensation. The equivalent U-value method assumes timber is spaced evenly across the wall, meaning it could possibly overlook the risk when timber studs are built up. But if the equivalent U-value method is not suitable, what tools are able to calculate this risk? Martin et al. Identifies two factors that increase the complexity of a tool and improve the tool's ability to replicate the behavior of thermal bridges. The first relates to modeling the thermal inertia of a thermally bridged building element and the material's ability to store heat. The second relates to replicating 2D and 3D heat flow that occurs due to thermal bridges. Baber and Prater argue the equivalent U-value method does not replicate the dynamic effects of heat flow through the thermal bridges, as it does not consider the material's ability to store heat. Prater and Momovic found the risk of condensation would be identified in a dynamic simulation tool, but overlooked in a static simulation. Baber found the opposite, likely due to the findings of Martin et al., who concluded static simulations cannot consider the thermal inertia or the possibility of heat traveling in both directions. This results in instantaneous heat flow through the building fabric. Therefore, static simulations can calculate greater heat flow when compared to dynamic simulations, as the possibility of heat traveling in both directions through the wall is not considered. These papers suggest that the method used in Clause E3 is likely to overestimate heat flow, resulting in apparent risk of condensation. The effects of using a one-dimensional simulation tool can underestimate the energy demand by 10 to 70%. Prater and Quentin and Feldheim found the use of one-dimensional modeling is inadequate and a 2D or 3D simulation tool should be used. Kalusak and Novak argue that even though the word multidimensional covers 2D and 3D, the results from using these methods can vary significantly. Earlier papers written by Posey and Dalgleish and Standard concluded that 2D simulations are sufficient to reliably calculate the surface temperatures, but more recent papers demonstrate the difference between calculated surface temperatures when using 2D and 3D simulation tools. If two-dimensional tools are used, the risk can be overlooked, as the calculated surface temperatures are warmer than what they would be in reality. This suggests the use of the one-dimensional method from clause E3 will overlook the risk of condensation. The impact of simplifying thermal bridges on the amplitude and phase lag of heat flow due to thermal inertia is well investigated. This is something that is affected by the conditions under which the tool simulates and the number of dimensions it models in. The findings from the review suggest the impact is determined by the material's thermal inertia. Baber concluded lighter materials, including timber, do not significantly affect the results when simplified. Mao and Johannesson conclude the same about metal studs. But Martin et al. Found the effect of simplifying a timber stud was significant when the thermal inertia of the wall was greater than that of the thermal bridge. These results suggest thermal inertia is important to consider with some materials, but can be simplified for others. Martin et al. Also states there is currently no single hybrid method that can replicate the dynamic behavior of thermal bridges of all materials. Regardless of the number of dimensions or the conditions under which a model simulates, the most common benchmarking tool used to identify the risk is the temperature factor. The risk is identified by calculating a value between 0 and 1 based on the internal and external air temperature and internal surface temperature. The risk is assumed to be insignificant if the value calculated remains greater than the critical temperature factor, but the value of the critical temperature factor is under debate in the literature. Mamovic and Standard use a constant value of 0.75 and 0.70 respectively to identify the risk. Pont and Madavi use 0.7 but also have two additional values. Their critical values suggest that surface condensation is not the biggest risk and that corrosion of metallic surfaces and mold growth would occur before condensation. Rather than using a constant critical value, Kalusak and Novak use an equation from the Czech technical standard based on the internal and external air temperature, internal relative humidity, and critical relative humidity. The Czech standard and ISO standard 13788 use 80% for the critical relative humidity to identify possible mold growth, rather than using 100% relative humidity, which would identify the point at which surface condensation would form. The findings from the literature review suggest there is a trend where the reliability of results increases as the complexity of a tool increases. Therefore, the use of a 3D dynamic tool is required to obtain the most reliable and precise results. The level of expertise required to run these programs is not likely to be found in a design construction office. When looking at the one-dimensional static method used in clause E3, findings from the literature review suggest this method may be oversimplifying the behavior of thermal bridges and inaccurately assessing the risk of condensation. But if the clause E3 method is too simple and a 3D dynamic tool is too complex, what tool is best suited for designers to use that could reliably assess the risk of condensation without requiring large amounts of time and experience? Further research needs to be done in this area to identify a tool that is good enough. Just for reference, the equations used to calculate the temperature factor and critical temperature factor are shown on the slide. Thank you very much for attending this presentation. Are there any questions?